Okay, welcome back for our notes for Chapter 13 for Advanced Placement Chemistry. We left off last time talking about first-order reactions and the half-life for a first-order reaction. Really the important thing for this is calculating half-life isn't all that difficult. It's really just finding the right formula to use depending on first-order, second-order, zero-order reactions. So here we're showing that the half-life for a first-order reaction is equal to the natural log of 2, which is 0.693 over K. So what's the half-life of N2O5 if it decomposes with a rate constant of 5.7 times 10 to the negative fourth? That would be your K. So it would just be 0.69 divided by that value. That'd give you a half-life in seconds. And so it'd look something like this. And it'd be about 1200 seconds. So there's how you could do a problem like that. So how do you know it's in a first order reaction? The units of K are seconds negative 1. If it were a second order reaction, it'd be molar negative 1 second negative 1. So that's one way to know it's first order. So first order reaction, A is developing the product pretty much independently of B. So the number of half-lives here, we're showing this graph here divided by 1. So if we go through 2 half-lives, it'd be 4. 3 half-lives, it'd be 8. 4 half-lives, it'd be 16. And that's the initial number of A divided by N, the number of moles product. So if we look at second order reactions, our rate is going to be A squared. You remember second order, we talked about a little bit in class, that as second order reaction, it's the concentration squared is what we had determined there. So here would be K is equal to our rate divided by concentration of A squared if it's second order. So it'd be molar per second divided by mole squared. So your units for K is going to be per mole second, or molar negative 1 second negative 1. And so again, it's kind of the right thing. We got to make sure we're using the right equation. And so for half-life, it will look like this. T1 half is 1 over K A sub 0, which is the A that we're starting with. And this graph shows us that the slope here is equal to K, our constant. So if we're using zero order reactions, then our rate's negative A over T, and the rate is only dependent upon K because the concentration of A, as odd as it seems, doesn't actually affect a zero order reaction. So we want to use our equation for a zero order reaction would look something like this. A at the concentration you're concerned with is equal to A at the beginning of the reaction minus KT. That'd be the equation for a zero order reaction. And we'll work with all of these in class. And so T1 half would be A sub 0, our initial concentration of A, divided by 2K, which is our rate constant. And so there the graph's a little different for zero order reactions. So here's the important slide. When you're asked a question about order or rate laws or half-lives, you make sure you find the right equation. If your zero order reaction, this is your half-life equation. If it's a first order reaction, then this is your half-life equation. If it's a second order reaction, then this is your half-life equation. That's kind of the important stuff. That's what we're going to be using in class to solve these kinds of problems. So here we're going to look at a reaction preceding A and B are our reactants, and C and D are our products. And so for this reaction to go from reactants to products, it has to form kind of this intermediate step where we're no longer A plus B, but we're not yet C plus D. And to get to that intermediate step, we have to get enough energy to make this reaction proceed. We call that activation energy. So in an exothermic reaction, our products have less potential energy than our reactants. So to get from reactant to product, overall, energy is released. When energy is released, it's an exothermic reaction. That's something you should hopefully be familiar with at this point. Here we have our reactants A plus B forming products C plus D, and our products have a higher potential energy than our reactants. So the net energy change is increasing. So this is a reaction that needs to absorb energy to occur. We call those an endothermic reaction. So hopefully that's old news to you at this point. From Gen Chem, The activation energy is the minimum amount of energy required to initiate a chemical reaction. So it's energetically favorable for A and B to become C and D, but unless we have this right here, E sub A, activation energy, around, we're not going to be able to form those products. So that's activation energy. So here's our rate constant and how it depends on temperature. Our rate constant, you can see with temperature increasing, our rate constant's increasing as well. So here's your formula for that. Your constant is equal to A times E raised to the negative activation energy divided by the gas law constant and absolute temperature. That's called the Arrhenius equation, where EA is the activation energy, that's in joules per mole. R is the gas constant, 8.314 joules per Kelvin mole. T is absolute temperature, so our temperature in Kelvin. And A is our frequency factor. So you can rearrange that to make it look like this if you needed to. So there are a few alternate forms. If it's at two temperatures, we can arrange it to this form here. We won't work with that very much. Or we could arrange it to this formula here, which looks very, very similar, except for this portion right here is all they've changed. So there's a way you can form or solve for activation energy if you have temperatures that an equation is occurring at. So that's kind of a neat deal. So it's very important for molecules to be oriented in the right direction for a reaction to occur. Here we have carbon monoxide gas and nitrogen dioxide gas trying to form carbon dioxide and nitrogen oxide, or nitrogen monoxide, I guess. And so here we want to get the carbon monoxide to be oriented so that the other oxygen is pointing towards the free end of that carbon. And if we do, we can get both those oxygens on the carbon and only have one oxygen on the nitrogen. So they have to be oriented in the correct direction. So here we're saying this is an effective collision. So they happen to bounce together in the orientation that they needed to hand that oxygen from nitrogen to carbon. If they had bounced the other direction, this might not have happened. So here we've got one where nitrogen's trying to give oxygen to carbon, but they hit each other, carbon to nitrogen. When they hit each other here, they can't hand off an oxygen because the oxygens are facing the wrong way. So we end up bouncing off and getting still carbon monoxide and still nitrogen dioxide. That's a pretty ineffective collision. So the shape of molecules has a lot to do with whether or not they're going to react. And that has a lot to do with activation energy. So the overall process, or progress rather, of a chemical reaction can be represented at the molecular level by a series of simple elementary steps, or elementary reactions. The sequence of elementary steps that leads to product formation is the reaction mechanism. This is going to feel a little bit like Hess's law when we get into it. So here we have nitrogen monoxide plus oxygen gas yields NO2. And so we know that overall these are our reactants and these are our products. But as we look at this reaction, we find N2O2 during the reaction. And you look at this and you say, well, N2O2 is not anywhere up here, so it must be an intermediate. From getting this to this, at some point, we must form N2O2 in the middle. And so we say, okay, let's say there's an elementary step. Maybe if we take one nitrogen monoxide and one nitrogen monoxide, we can form that N2O2. That's our first step. Then after that, we take that N2O2, react it with oxygen, and we end up getting NO2 out of that, because of course that'd be, two nitrogens and four oxygens, and that's what you'd have here, two nitrogens and four oxygens. So we say these two elementary steps together, they give us the overall reaction. And so our overall reaction is 2NO plus O2 yields 2NO2. We can cross this off, kind of like Hess's law, to give us this. But we know that it has to occur in these shorter steps. So something interesting. There they're crossing out the same thing, repeating itself on different sides of the arrow. So we can say here's what our reaction mechanism could look like. First thing that has to happen is two of our nitrogen monoxides have to make this dinitrogen dioxide molecule. Then a dinitrogen dioxide molecule has to react with oxygen gas to give us two nitrogen oxides. So intermediates are kind of our N2O2 example, are species that appear in a reaction mechanism but they're not in the overall balanced equation. So that's our N2O2 example. The intermediate's always formed in an early elementary step, and it's consumed later in an elementary step. So here it's formed early, it's consumed later, so it doesn't show up down here. There is no N2O2. And there's your intermediate. So this gives us this odd term, molecularity. The molecularity of a reaction is the number of molecules reacting in an elementary step. A unimolecular reaction is an elementary step with only one molecule. A bimolecular reaction is an elementary step with only two molecules. And a termolecular reaction is an elementary step with three molecules. So here we have 1, 2, 3, termolecular, 1, 2, 3, termolecular, all sorts of odd terms. So, rate laws. How do these apply to elementary steps? Well, in a unimolecular reaction, A goes and forms our products, so our rate's only dependent upon A. In a bimolecular reaction, A and B both together form our products, so our rate's probably dependent upon our constant and the concentrations of both A and B. In a bimolecular reaction, it could be A plus A yielding products, so it would be only equal to the rate times the constant A squared, because we're showing that our concentration of A is dependent upon, or rather our products, are dependent upon the concentration of A squared, because there's twice as much as there should be. So it can help us write some plausible reaction mechanisms, like the sum of the elementary steps have to give the overall balanced equation for the reaction, and the rate determining step should predict the same rate law that is determined experimentally. So a rate determining step is going to be the slowest rate. The rate determining step is the slowest step in the sequence of steps leading to product formation. If your goal is to run a relay, perhaps, and what matters is the team time in the relay. Let's say it's a 4x1. Your rate determining runner is your slowest runner, because who determines how fast or slow you finish the race is going to be kind of dependent upon your slowest runner. You can only be as fast as a team as, that slowest runner and his leg. He's the rate determining step. So, sequence of steps. When we study this reaction mechanism, we look at the rate, we get the rate law from the rate, and then we try to look at what's a reasonable way we could make this molecule. And so here's an example of how you might do that. We say, okay, our experimental rate law for a reaction between nitrogen dioxide and carbon monoxide to produce nitrogen oxide and carbon dioxide is a rate equal to the constant NO2 squared. The reaction is believed to occur through two steps. Step 1, NO2 and NO2 form NO and NO3. We take those products, we say NO3 from here, plus carbon monoxide gives us NO2 and CO2. So what's our overall reaction? We can cross out NO3, NO3. We can cross out, looks like maybe NO2 and NO2 as well. And then we'd have something like this. Oh, perfect. NO2, carbon monoxide, gives us NO and CO2. So what's the intermediate? Of course, NO3. And so what can we say about the relative rates of steps 1 and 2? Well, we can say the rate for the K NO2 squared is the rate law for step 1. So step 1 must be slower than step 2, because our rate is for NO2 squared. So our rate's dependent upon this guy. And if our rate's dependent upon him, he must be the slowest. That's the idea. This little slide's about femtochemistry. It's basically chemistry of super short progress, super short amount of times, how molecules can change in a very tiny amount of time, like 10 to the negative, 15th or 16th second, something like that. And it's a way of showing that to get from one organic molecule to another organic molecule, these are the intermediates that are formed. And they're kind of showing you some different shapes here. To get from here to here, we form this very odd box shape with these unbound electrons up here. So it's just kind of that example trying to show you that to get from point A to point B, sometimes there's a point in the middle that doesn't really make sense. So A catalyst, hopefully, is a term you're a little familiar with. It's a substance that increases the rate of a chemical reaction without being consumed. Here's our chemical equation again that we saw just a little bit earlier for the Arrhenius equation. And a catalyst is going to decrease this right here. It's going to decrease that activation energy. And if you decrease the activation energy, you increase the K, or the rate. So we're increasing the rate, making it much faster. So here's an example of an uncatalyzed and a catalyzed reaction. If we can shorten up that activation energy with a catalyst, we can make this go a whole lot faster than without a catalyst, how you'd have to have just a ton of activation energy to reach. So I do believe these two are switched, because a catalyzed reaction should lower the activation energy quite a bit. So the rate of our catalyzed reaction will be much quicker than the rate of the uncatalyzed reaction. So here they're showing EA catalyzed is less than EA, activation energy. So heterogeneous catalysts, the reactants and the catalysts are in different phases. So the Haber synthesis of ammonia, the Ostwald process for the production of nitric acid. You can see all these examples in your book. Catalytic converters, of course, the reactants are gases, exhaust from the engine, and the catalytic converter is like a plate, a metal plate with, I think, tiny ceramic pores. So you have a solid catalyst with gaseous reactants, heterogeneous, just different phases really. And if it's homogeneous catalysts, the reactants and catalysts are dispersed in a single phase, normally a liquid. Acid catalysts, like acid batteries, for example, to make that reaction occur quickly. They're both liquid phases. Base catalysts, same idea. So here's a picture of the Haber process, the way we make ammonia. They're showing you the catalyst here: iron, aluminum oxide, potassium oxide. Here we've got nitrogen and hydrogen, nitrogen and hydrogen. Not very likely to react with each other, they're both very stable. But when we get them on this catalyst, this plate of iron and aluminum oxide, they'll form those NH3 bonds. That ammonia is very important. We use it to make fertilizers and all sorts of stuff. Ostwald process, here's ammonia and oxygen making nitric oxide and water. Here they use platinum catalyst, and here you can see, kind of cool, this is this huge platinum catalyst solid used to go ahead and make that nitric oxide out of. It's kind of cool. And here it shows you the reaction, simplified NO oxygen and 2NO2. And then here at the end, that NO2 from here, this intermediate that we talked about before, is going to react with some water, make HNO2 and HNO3. So we can make a nitric acid using the Ostwald process. And then here's the catalytic converter, exhaust, coming out of an exhaust pipe, going through a couple catalytic converters. This is a pretty environmentally friendly car, it has two, and then finally out the tailpipe. We're trying to get those kind of nasty chemicals sort of reduced down to like water, carbon dioxide, that kind of stuff. Carbon monoxide, not so good. Partially combusted hydrocarbons, not so good. All sorts of stuff. So we're going to take that, combine it with oxygen to those catalytic converters, try to get it to CO2 and water if we can. It's going to be the best for the environment. Then here's a picture of the catalytic converter. Ton of surface area in there. It's super, super hot, and it just tries to complete the reactions that didn't have time to complete in the pistons, because when the gas is combusted in the pistons, that's a very, very short time that it's allowed to react. So then here's another reaction that's occurring in here. The nitric oxide, not so great for the environment. Nitrogen dioxide, not so great for the environment. Nitrogen gas, not bad. 78% of the atmosphere, give or take. So we can have that. Oxygen gas, not bad. We can have that. As cars become a little more environmentally friendly, you will see vehicles that have multiple catalytic converters in them, and that's probably a very good thing. If you see a big diesel truck take off from the stoplight, and all of that big black smoke stuff rolls out of the exhaust, that's this part right here, the unburned hydrocarbons. Those guys are pretty persistent in the atmosphere, and they're pretty nasty stuff. So if we can get to this and less this, then we might just do okay in the world. So that's a catalytic converter. Here's one I like, because I'm a biology nerd. This is finally something I understand in this book. Enzymes all over in your body. Enzymes are catalysts in biological organisms, and the enzymes fit a substrate, and only this substrate fits the enzyme. There might be other things that are close to it, but none fits like this. And the enzyme takes a substrate that might take a very, very long time to break apart and will break it into products. The reason that you and I are able to digest all sorts of foods and create all sorts of proteins and all these things that keep us alive is largely because of enzymes. If we had to wait for our food to break down naturally just by chemical bonds breaking because chemical bonds break, it would take years. But we can digest a whole meal in hours because our body's full of enzymes that do just this job right here. It's pretty amazing. So again, lowering the activation energy to speed up the rate at which we get products. Our life depends on it. That's kind of a nice thing to have around. Here's an example of glucose binding to a protein. Huge protein, look at that thing. Hexokinase, kind of cool. Glucose fits very closely in the enzyme. The enzyme changes shape just a little when it binds to the substrate it's interested in. So, enzyme kinetics. This is an example of our rate depending on pressure. Here, the delta pressure over the delta time affects our rate. So our enzyme plus our substrate gives us the enzyme substrate compound. And then that breaks apart to give us our enzyme and some products at the end. So our rate's dependent on our products divided by time, and the rate is equal to the constant multiplied by the enzyme substrate combination. And so the rate does kind of have a maximum. You see that as we add more substrate, our rate increases quite a bit, and then it kind of levels off. We get to a point where all of our enzyme sites are full. And when they're all full, it doesn't matter how much substrate you add, there's no more enzymes to work. So they can only work at a particular rate. If you change things, temperature, pH, you can affect that for better or for worse. But at your normal body conditions, there's a maximum output. So no matter how much substrate you kind of pour in,